Hello students, in this video we will consider the greatest common factor and factoring by grouping. First, let's note the process of multiplying. 6 times 2 is equal to 12. And in this, the 6 and 2 are factors. The 12 is a product. The product is the answer to a multiplication problem. Now, we're going to consider the reverse of multiplying, which is factoring, where we take a product such as 12 and we write it as multiplication in multiplying the factors 6 times 2. So to factor a number means to write it as a product. And that is our focus today. Quick reminder, a prime number has only itself and 1 as factors. Examples of prime numbers are 2, 3, 5, 7, 11, 13, 17, and so on. Our steps for finding the greatest common factor, or GCF, are to factor, write each number or term in prime factored form. So we're going to be using some prime numbers from this list above. Step 2, list the common factors. Step 3, choose the least exponent for each common factor from step 2. And step 4, we're going to multiply the primes from step 3. For example, find the greatest common factor, or GCF, for the numbers 24 and 36. Well, I'm going to begin to factor this into its primes by using a factoring tree and starting with any factors of 24, such as 4 times 6. Neither of these is prime. 4 is 2 times 2 and 6 is 2 times 3. Therefore, we can write the number 24 as 2 times 2 times 2, that's 2 to the third power, times 3. Now let's do the same with our number 36. 36, now we can say that that is 4 times 9. 4 is 2 times 2, and 9 is 3 times 3. So we can factor 36 as 2 times 2, that is 2 squared, times 3 times 3, or 3 squared. So now that we have each of these factored into its primes, we're going to list the common factors. So our greatest common factor contains the factor 2 as well as the factor 3. Those are common to both factorizations. Now we'll choose the least exponent for each of these from step 2. As we look at this factor 2, 2 is the least exponent, and 1 is the least exponent for our common factor 3. Now we're just going to multiply these primes from step 3. Our greatest common factor is 2 squared, that is 4 times 3, or 12. Now another way that you might find a greatest common factor is to list the factors of 24 and list the factors of 36, and then just identify the largest factor in both lists. And there you would arrive at 12 as well. Well, let's look at part B. Still, we want to find the greatest common factor, and let's use a factoring tree for 18 also. 18 is 2 times 9, which is 3 times 3. And so 18 x to the 5th, y to the 7th z in prime factored form is 2 times 3 squared times x to the 5th, y to the 7th z. Now as we factor 36, I'm just going to look back here at our previous problem and use our results there. 36 is 2 squared times 3 squared, and our variables are x to the 4th times y. Likewise for 24, let's look back at part A we know that 24 factors 2 to the third times 3. And our variables, x to the 7th, y squared, z to the third. Now, as we determine our greatest common factor, it's going to include every factor in this list, so that's common to both, 2 and the 3, x and y, but z isn't common to all three of them, is it? So it's not included as in the greatest common factor. Now we go with our least exponents. The least exponent attached to 2 is 1. Same for 3. Let's write x to the 4th power and y to the 1st. And thus our greatest common factor of these three terms is 6 x to the 4th y. Let's look at another one, part C. Still we're finding the greatest common factor. Let's use our factoring trees. 90 is 2 times 45. 45 is 5 times 9. And 9 is 3 times 3. Therefore, 90 factors 2 times 3 squared times 5. $144. I'm going to begin with factors 12 times 12. And note here that it doesn't matter what two factors you begin with. Just go with any two that you can think of and then proceed from there. Now, each of these 12s is 3 times 4. And each of those 4s factors as 2 times 2. 144 in its prime factored form, 2 to the 4th times 3 squared. And then lastly, 288. Well, that's 2 times 144, isn't it? And so our factors of 144 are then exactly what we see in our previous tree for factoring 144. So we can conclude that 288 is 2 to the 5th times 3 squared because it has one additional factor of 2 beyond the 144 factorization. Now as we write our greatest common factor. It includes every common factor that we see in the previous factorizations. So it includes 2 and 3, but not the 5. Along with our least exponents, so that will be a 2 to the 1st times 3 squared. 3 squared. So that is 2 times 9 or 18. So go with your smallest exponents each time. Now as we look at example 2, we're actually going to perform our process of factoring an expression by factoring out the greatest common factor. As we look at part A, the numbers 18 and 36 have greatest common factor 18. So we're going to factor that out of each term. 18 times y gives 18y plus 18 times 2 gives 36. So we've rewritten this sum as a product, 18 times the expression y plus 2. In part B, as we determine our greatest common factor, looking at our numbers first, 125, 60, and 85, they all have a common factor of 5, but that's going to be the largest. Now, if you need to use your process of determining a greatest common factor here, go ahead, all right? But the greatest common factor of those numbers is 5. As we look at our variables, each term has at least a to the 3rd. Each term has at least b squared. Now we complete the factorization. 5 times 25 is 125. We've got a to the 3rd, but we need 3 more b's. And we can always check by multiplying. 5 times 25 is 125. A to the third, and adding exponents, that's b to the fifth. Moving to our next term, 5 times 12 is 60. We need another a factor and 2 more factors of b. Last term, 5 times 17 is 85. We need 2 more factors of a, and we've got a sufficient number of factors of b. Again, remember that we can check all of our factorizations by simply multiplying back and making sure that we get that original expression. Lastly, part C, this one's unique. We essentially have 2 terms, and the common factor in each term is x plus 2. So we're going to factor out that x plus 2. X plus 2 times x gives our first term. We've got a plus sign in between, and x plus 2 times 5 gives that last term. And this is a precursor to some factoring that we're going to do next. In example 3, we're going to factor by grouping. So in each of these cases, we've got 4 terms. And we're going to first note that there's no greatest common factor for any of these expressions to factor out. However, if we just let our eyes group these in pairs, then we can begin by factoring a greatest common factor. The greatest common factor of m squared plus 2m is m. So let's factor those first 2 terms as m times m plus 2. Now as we look at our second 2 terms, there's a greatest common factor n. Now notice that there's a plus sign in between here, isn't there? Don't lose that. Let's write these second 2 terms, n times m plus 2. And now we've got 2 large terms here with a common factor m plus 2, which we're going to factor out. M plus 2 times m plus n. And how do we check this? Well, we can check it by multiplying back, and let's just do that quickly. M times m is m squared. Outer product m times n. Inner product 2m. And lastly, plus 2n. So as we multiply those binomials, we get precisely the expression that we started with. So we know we've done that correctly. In part B, our first 2 terms have common factor y. Y times y minus 6. Second 2 terms have common factor w. So let's write, plus w times y minus 6. And when we are factoring by grouping, we want to see this repeated factor so that we can proceed to this last step. Factoring y plus 6 out of each term times y plus w. Check by multiplying. Part C. First 2 terms, common factor 2a times a minus 2. Second 2 terms, common factor 3b times a minus 2. And then we're able to proceed because we've got that repeated factor a minus 2 that we continue to factor out. A minus 2 times 2a plus 3b. Two more here, part D. Common factor of our first 2 terms, x squared times x plus 3. Now with our second 2 terms, as we factor, we want to repeat a positive x plus 3, don't we? So we're going to factor out negative 5 and pull that negative symbol with the 5, okay? Because negative 5 times x gives negative 5x, and negative 5 times positive 3 gives that negative 15. And this allows us to repeat that common factor x plus 3. Continue factoring x plus 3 times x squared minus 5. And check by multiplying, okay? Last problem, part E. As we jump into this and begin to factor by grouping, let's say we look at our first two terms and, there's a common factor of 2 times 3y squared minus 10w. And our second two terms have common factor y times 15 minus 8w, but we've got a problem here, don't we? Our in parentheses in each term, those factors aren't the same, and so we cannot proceed to the next step. So that didn't really work out, so let's come back to the drawing board and try something different. I'm going to rearrange terms here and just transpose these middle two terms and rewrite this expression 6y squared plus 15y minus 20w and minus 8yw. Now, what I see happening here is now our first two terms have a common factor that includes the variable y. In fact, that greatest common factor is 3y times 2y plus 5. And as we factor out our greatest common factor of the second two terms, let's factor the negative symbol along with 4w. Multiply that times 5 and plus 2y. Let's just check that. Negative 20w minus 8yw. Now, as we look at what we have in parentheses in each term, those are the same, okay? We know that addition is commutative, isn't it? 2y plus 5 is the same, equivalent to 5 plus 2y. So we can finish this and complete the process. We're going to factor 2y plus 5 to the front, okay, times 3y minus 4w. Again, remember that we can check these via multiplication. So there we've looked at greatest common factors, factoring out a greatest common factor, and factoring by grouping.